I need to preface this by saying I may have forgotten that I was supposed to do this because I thought it was in the fall convention, but that's okay because Clippy came to save me. The good thing is I've done this project for 4 years now. I've taught over, in this case, about 350 students in this project, so it wasn't actually that bad coming up with the presentation. So when we think about laboratory activities, we think of them, and we have done them for a while, as independent activities. And what I mean by that is, and I want to talk about materials, we do a sieve analysis. Great, we get a gradation. And then we may move on to steel tension, or we may do a soil test. But we rarely relate them all to a single project so that the student throughout the semester is like, okay, now I'm seeing where all these test values are going. When I was in undergrad, yeah, each test we did was, okay, we do the test, we write the report, turn it in, and then we never really talk about it in the next test or the whole semester in terms of an overarching theme. Now, the nice thing is, that's pretty low cognitive load for the student because they're not having to think beyond what they're doing. But on the same time, that's actually kind of bad because we want them to be thinking. And it only gives them kind of really that one touch for that topic, and then they don't often see it again in the semester. And the other thing with labs is, and I've heard this, hey, I have a lab, it's automatically experiential. No. It's actually quite easy to design a lab that is not experiential because it is so prescribed that the students actually aren't experiencing something. Now, I have ABET on my mind because on Wednesday I fly to the ABET symposium. I'm responsible for our department's self-study report, and we have 4 accredited programs in our department, so I have to write 4 separate reports. I'm very much in tune with ABET. You may not know what all the outcomes are, and that's fine, but I highlighted one word in outcome 6, which often is applied to laboratory-based courses. The word develop. If you give your student a mix design and say, all right, you're going to mix concrete, here's what you're mixing, we're going to measure strength later. Well, the student actually didn't develop anything. They followed a recipe. They followed instructions. There was no development. They did conduct it, that's true, and they analyzed, they did everything else except develop. So, today I'm going to talk about how I get students to develop something in a laboratory course. And here's the course. It's sophomore level, which is very challenging compared to grad students that use, oh yeah, go do whatever you want. No, you can't do that with sophomores. It's 3 credit hours. I have about 90 students a semester. Our program is top 10 for overall enrollment. We have over 800 undergrads in our program. This can be done at scale. And this is the first civil engineering course the students are taking. So it's really important from a retention standpoint that we allow them to see that they have the ability to succeed. And so we're not doing anything super special for the majority of the semester that any of you who teach a materials course wouldn't do yourself. Sieve analysis, measuring relative density of aggregates, steel tension testing, mixing concrete, testing strength. We're doing all those. But here's a little thing that we're adding or connecting the dots with. The sieve analysis they're doing is the aggregates they're going to be using for concrete. And the students have to use their own gradation when calculating the fineness modulus to follow ACI 211 to get the mix design. Even though it's the same aggregate source, they all have different fineness modulus because they make mistakes in the sieve analysis. And my role and the TA's role is to make sure the mistakes aren't too big, but we're not correcting them and saying, all right, guys, you did a sieve analysis, but ignore all those numbers and here's the real numbers. As long as their values are kind of ballpark, we're going to let them go with it because it's one point when they write their final report that they can say, yeah, we probably missed that, and that's why our mix didn't turn out well. Same thing with the relative density, steel tension, and so forth. So we're going to have all these common labs that pretty much every university does, but all tied to the same project. And that project is, I call it Will It Tornado, where we have a debris cannon on campus. I think now we're the only campus in the United States that has an active debris cannon. We can shoot 2x4s at like 200 miles an hour. I lower it to 150 for the students because at 200 it starts getting a little wonky. But they're going to design a concrete mix using all the properties they've measured, make a panel, have reinforcement, and there's some scoring and economy of design. And some semesters, because this was actually partially sponsored by PCI Studio, we have thin brick inlay, so they get to see how physically their mix interacts with the thin brick. Some of them aren't well designed and they don't work well, but they're making this. They're doing everything. So when we think about setting this up for a semester, especially with 90 to 120 students, we got to think about, okay, what are the students going to see throughout the semester? It has to be somewhat planned from the instructor side. The students need some plan, but it's not as important except having a good explanation of the theme and the project they're doing. And so we get those core properties that they need early on, even before sometimes we talk about it in lecture, so that they are seeing it and constantly like, okay, I have some values, I'm going to use those later on. And we're going to keep touching on them throughout the semester. Because if you can build upon knowledge rather than setting these knowledge like stumps along the way, we can build up rather than out, they'll have a deeper understanding of the content. Now there's an argument to say, well, if you do it that way, you can't cover everything. And that's absolutely true. I don't cover as much as a lot of the materials textbooks have. And I'm okay with that because my students come away with what I would consider a deeper understanding and ability to succeed in future courses. Because in my institution, this is their first course that they really need to see how to start thinking like an engineer. And so I'm not really in the lab teaching, it's more facilitating, asking questions. They're using their own values, which are probably wrong, which is okay, because it gets them thinking about, all right, I should have maybe not spilled that whole sieve out, and that's why I have a gap in the gradation. And they're connecting those dots rather than everything being so perfect that, okay, it's going to work. And the other part is giving them some space. So when you actually are doing something like this, it can't be just back to back to back to back because your brain needs time to process the material. They have other courses they're taking, especially at the sophomore level. A lot of them are taking still their last calculus. They're taking mechanics of materials, maybe dynamics, fluids. Like they have a lot of other courses that are needing their attention. And so instead of doing these huge just chunks of material, giving it some time to process and space out is going to be really important. And I like highlighting actual research that backs up what I'm saying, and this is just one paper. There's a lot out there that you can combat that natural forgetting curve by just coming back to things. Just because you said it doesn't mean they got it, and doesn't mean they should, honestly, in my opinion. You shouldn't expect them to just magically know 3 months from now in the final exam what 2 sentences you said in lecture 3. You have to kind of touch on things. And we're engineers, we like actual data, so here's from that same reference some actual data. Now you could say, okay, well the scatter is not statistically significant increase. Well, in education research, you rarely get something that will statistically separate itself, especially looking at knowledge retention. So this is pretty darn good. So encourage you. This is actually a really good paper. That's why I picked that one. It's pretty easy to read. And I'm going to reinforce this part too, is the actual cognitive load on the student during the lab activity. So I said if you just say, all right, here you're going to mix concrete, here's the steps, you go do it, the load is not that high, they're not thinking. But on the flip side, and I'm going to pick on Dimitri here, if you just say, oh, go do this, just tell me what you get, that's a very high cognitive load. And for sophomore students who have never taken an engineering course, that's too high. And it's not just because of the material. They're interacting with their peers who, again, this is the first course they're taking. That's stressful. They don't know, oftentimes, the other people in their group. The fact that you could potentially ask them to do something on their own is stressful because, again, all their courses up to that point are grading them very strictly on performing. And if they don't have that trust with the faculty member that, hey, it's okay if you mess up, they're going to be stressed, which is reducing the available cognitive load they have to actually do the lab activity. So there's a lot that goes into this. Again, another great reference that you can look at. But coming back to things helps with this. Because if they didn't get it the first time, because their cognitive load was just used up, the next time they see it, they may be in a slightly better place and may actually process it a little bit better. Okay, so we do all that. We have this overarching theme of Will It Tornado, class project, 90 plus students in 20 groups. What happened? Well, this course, and I realize DFW may not mean, that means the student got a D, F, or withdrew from the course. So this course historically had 20 to 30% DFW rate. It was the highest one almost in the college. And I dropped it to 10 to 15%. I say I because I'm not the only one who teaches this course, and the other instructor still is at a higher rate. He is here. I forgot. He bought a ticket. Okay, yeah, well, he's not in the room. But don't tell. Anyway, so it dropped, which is good. Upper administration always likes seeing great retention rates. And the next thing is the biggest, in my opinion. They no longer complained about labs. They actually wanted to go to the lab. They got so excited that they were going to make something that they could shoot with a cannon that they were literally motivated to do well. And they don't realize it, but that's actually increasing their learning ability because they want to do it. And they developed it because I didn't give them any answer. What they came up with was what they came up with their data that they measured. They developed from scratch a concrete mix to put into a panel with some reinforcement that they chose, and then we conducted the experiment on it. It's really hard actually when you read ABET's guidance on this, on how you can get students to demonstrate they develop an experiment in an engineering curriculum. And that's why I think a lot of the PEVs that visit programs and accredit them, maybe just kind of check the box because it's kind of hard to actually show that. Now, I've done this a lot, and here's just some slow motion video. That's real-time video. I put it as a GIF, so it's only 6 seconds on loop because I didn't know if the video would embed. But each group gets tested. We have 2 high-speed cameras that film it. Sometimes I let the student press the big red button to shoot the cannon. But I show this at the start of the semester so they kind of see what they're shooting for. And this is what really, I think, sets the tone for them buying into an entire semester of labs that all tie together. Because if I just said, hey, you're going to do all these labs, and then you're going to do this huge project at the end, every sophomore's like, oh my gosh, are you kidding me? But now we're putting it into this context that it's actually going to be something fun, but they're buying into, okay, now it's mine. It's my panel. I made it. I'm going to actually be able to do this. So reduce cognitive load by spacing out things, build things up, and do stuff really cool. Get them to buy into science. It doesn't have to be a debris cannon project. There's other projects, the beams. When we have, I know Shri does like big beam. Oh, the students love that. I don't know exactly what's involved with it, but I know it's hands-on. It's, they get to see from start to finish their design. But he keeps touching on things. And that's the same thing here. Is not just, all right, here, you do this activity, you do this, and they're independent. It has to tie together and actually build upon one another. So that is what I had.